Everyone in crypto talks about innovation, but few topics expose the system's weaknesses like cross-chain bridges. Billions of dollars have been stolen. Chains keep multiplying, assets keep fragmenting, and bridges keep getting hacked. So the question is simple. After years of failures, can we finally build bridges that are actually secure? Let's start with the basic problem. Every blockchain is an island. It has its own consensus, its own validators, and its own view of the world. Bitcoin doesn't know what's happening on Ethereum. Ethereum doesn't know what's happening on Solana. To move assets or messages between them, we need a middle layer, a bridge. And that bridge must somehow convince two separate networks that the same asset exists on both sides without being duplicated or faked. That's where things go wrong. Bridges exist because users want liquidity to move freely. You might want to use your ETH on another chain for cheaper gas or to access an app that doesn't exist on Ethereum. So a bridge locks your ETH on one side and issues a wrapped version on the other. It sounds simple, lock here, mint there, but in practice it creates a huge attack surface. If an attacker compromises the bridge, they can mint tokens without locking anything, effectively creating money out of thin air. We've seen this play out over and over. In 2022 alone, cross-chain bridge hacks cost the industry over $2 billion. Ronin, Wormhole, Nomad, Horizon. Different names, same problem. Trusted multisigs, poor validation, or replay vulnerabilities. And because bridges often hold enormous pooled value, they become perfect targets, the digital equivalent of a central bank vault guarded by just a few keys. So why is this problem so hard to solve? Because blockchains don't naturally trust external data. Each chain is a closed system that only believes its own consensus. To verify something from another chain, you either replicate its consensus, which is expensive, or you trust an external party to tell you the truth. That's the tension. Trust versus cost. The more you reduce trust assumptions, the more complex and resource-intensive your design becomes. Let's look at the main categories of bridges. The first are trusted bridges, basically multisigs or federations. They're fast and simple, but require users to trust a small group of signers. If those keys are hacked or collude, the bridge fails. This model worked temporarily in early DeFi, but it's the weakest in terms of security guarantees. Next are light client bridges, which use cryptographic proofs to verify events from one chain on another. They replicate part of the source chain's consensus logic inside the destination chain. It's trust minimized but expensive, especially when proof verification requires heavy computation or storage. Cosmos's IBC is a good example of this approach. Each chain runs a light client of the other, verifying headers directly. It's secure, but it only works well between compatible chains that can understand each other's consensus. The third category is hybrid bridges, using proof aggregation, relayers, or restaked validators to verify events. They try to strike a balance between security and efficiency. Eigenlayer-based bridge validators or shared security models belong here. They're not fully trustless, but they improve accountability. If a validator lies, they can be slashed. So what's changing now? After the chaos of 2021 to 2023, the industry realized that the bridge problem isn't just a side issue, it's core infrastructure. If users can't move liquidity safely, the entire multi-chain world collapses back into isolated silos. That's why a new wave of innovation is happening around message passing and native verification. Projects like LayerZero, Hyperlane, Wormhole 2.0, and Axelar are moving away from token bridges and toward general message bridges. Instead of just moving assets, they move verified data. For example, when you send a transaction from Ethereum to another chain, the bridge relays a proof that a certain event happened on Ethereum. The receiving chain checks that proof through multiple independent verifiers before accepting it. The asset transfer is just one possible message, but but the infrastructure is more flexible and secure. LayerZero uses two independent entities, an oracle and a relayer. Both must agree for a message to be accepted. If one is compromised, the message still fails. Hyperlane uses sovereign consensus, letting each app choose its own security level, from a small trusted set to full light client verification. Wormhole rebuilt its network with a larger, restaked validator set and real-time audits. Axelar uses delegated proof-of-stake with cross-chain finality proofs. Different methods, same goal: reduce the single point of failure that doomed earlier bridges. Another promising direction is native interoperability. Instead of separate bridges, some ecosystems are being built with cross-chain communication baked in. Cosmos IBC, Polkadot's XCM, Avalanche subnets, and even Ethereum's upcoming rollup ecosystem all aim for native trust. If rollups share the same settlement layer and data availability, moving assets between them doesn't need a risky external bridge. It's just an internal state update. The future may look more like that. Fewer external bridges, more shared security domains. Ethereum rollups connected through shared sequencers and canonical bridges. Cosmos chains communicating via IBC. Maybe even modular DA layers verifying each other through restaking or zero-knowledge proofs. The dream is simple: universal interoperability without trusted middlemen. But even in this new world, the rules don't change. No bridge is 100% safe. Every system still balances three things: trust, speed, and cost. If it's fast and cheap, it usually adds some trust. If it's slow and expensive, it's closer to trustless. Users must understand what they're trading off. So how do you evaluate whether a bridge is secure? Here's a simple checklist. 1. Who verifies messages? Is it a multi-sig, a validator set, or an on-chain proof? 2. Can the verifier be slashed or punished for lying? 3. How is the data delivered and confirmed? 4. Can you independently validate what happened without trusting the bridge's website or UI? 5. How quickly can an exploit drain funds, and can withdrawals be paused in time? If you can't answer those questions, you're not using a bridge, you're using hope. And hope has been the most expensive security model in crypto history. Still, progress is real. Bridges today are far more sophisticated than 2 years ago. Shared security, restaking, and zero-knowledge proofs are bringing verifiable trust to cross-chain communication. The ultimate goal is that bridges fade into the background. You won't even think about them. You'll just send assets or data across networks, and the system itself will guarantee safety. Can we completely stop cross-chain hacks? Probably not. But we can make them exponentially harder. The next big exploit won't come from a naive multisig. It'll target subtle implementation bugs or governance flaws. That's still progress. The goal isn't perfection, it's resilience. So here's the takeaway. Don't judge bridges by speed or TVL alone. Judge them by verifiability, accountability, and recovery. In the end, the bridges that survive won't be the flashiest. They'll be the ones that quietly connect the system without ever breaking. Because real innovation in crypto isn't about hype, it's about reliability. And reliability is what turns fragile experiments into real financial infrastructure. This is not financial advice. It's a framework to help you cut through the noise and see which bridges are moving from risk to resilience and which ones are still one bug away from history.